Let's look at the dynamics of simple harmonic motion. Here we have the motion diagrams, and for the particle of the mass attached to the spring moving to the right, and here moving to the left. And things to notice when when the mass is at position x equals 0, the acceleration is 0. When the is at the maximum amplitude, at the maximum position at A, then the acceleration points the other way and is maximum. And when the particle is at minus A, then the acceleration points in the positive direction and is maximum too. So we can try it and see why is this by looking at the derivative. Remember the position of the harmonic oscillator. The position xt is equal to a cosine omega t, and then the velocity vt is equal to the derivative of this, which is minus omega a sine omega t. So now the acceleration would be the derivative of the velocity, dv dt, which is the derivative of this thing here, and that'll give you the derivative of the sine, which is the cosine, and then there's an omega that comes out, so you get minus omega squared a cosine omega t. And if you compare this with this equation here, then you can simply write that the acceleration is minus omega squared x. So basically this is the position here, this is the position, and then you see this is the acceleration. When the position is maximum, when the position is A, the acceleration has the negative maximum here and goes uh, up and down with the same frequency as the position. So this comes from using Newton's second law. Remember, the force on the spring is equal to minus k delta x, where delta x is this distance from equilibrium to where the particle is located, because and this delta x would be just x because the equilibrium position is 0. Then you can write Newton's second law as the net force, which is minus kx, right? That is the force due to the spring. That has to be equal to mass times acceleration. This is Newton's second law. And from here we can write that the acceleration is minus k over mx. So now from the previous slide, you remember that a was also minus omega squared x. So then we can compare these with this quantity here and come to this conclusion that omega is the square root of k over m. We already saw this when we looked at energy, and this is the same equation that we had there. So let's look at a simple question here. A mass oscillates on a horizontal spring. Its velocity and the spring exerts a force F of x. The velocity is v of x, and the force of the spring is F of s. At the time indicated, at this time here, right, Vx is positive and the force is positive, Vx is positive, force is negative, Vx is negative, the force is 0, and so on. Choose one answer here, take a minute. And the answer is that Vx is 0, right? Because this is the maximum point. And the force is positive, right? Because all the the position is negative, so the acceleration is positive, so therefore the force is positive. So then we have a mass again that oscillates on a horizontal spring, velocity being Vx and force Fx. So at this time now, right here, which one of these is true? Take a minute. And now you can see here, well, the velocity is negative and the force is 0. The acceleration at this point is 0. The position is 0. The acceleration is 0. So it is this one here. And the velocity is negative because, well, it is the x is decreasing here. It's going from a positive number to a negative number. Okay, thank you.